showing the result of a measurement of the performance of a database management system. Two versions, called the old and the new. On the y-axis, we have the value of the metric, which is here the execution time. And on the x-axis, we simply have the instance of the job. Here, the load is a standard benchmark. I just realized that I was forgetting to record, but Hossein did it. Thank you, Hossein. So here I'm showing the raw data, and it looks like the old is performing less well than the new because the clouds are, the red cloud is a bit below the blue cloud. But how do we typically summarize this into something more quantitative? One classical answer is the histogram. So if we want complete information, instead of having a cloud of points, we can put a histogram. A histogram is obtained by taking a number of bins. By default, the plotting software I'm using uses 10 bins. And on the y-axis, we have the count of how many instances fall in this category. For example, here we have 22 or so points in the blue cloud that have a value that is between 0 and 10. Which corresponds to that part of the curve. Histograms are typically used also in probability, where we could plot on the y-axis not the count, but the frequency, the number of objects divided by the total. That would just be a rescaling here. The histogram tells us a lot. For example, we see here the distribution on the left is more diverse than the distribution on the right. The right is more compact here, but still makes the comparison difficult. So one technique that is often used if you need to compare two data points in a very synthetic way is to use what is called an empirical cumulative distribution function. Empirical distribution function is the equivalent of the CDF when we have an exact distribution, cumulative distribution function. When we have a set of data points, it is simply given by this formula. For every value of x, so it's a function, so we can plot it for every value of x on the x-axis. The x-axis is the quantity of interest, for example, in our case, the execution time. And for every value of an arbitrary parameter x, which is in the same space as the execution time, we count how many instances had a value less than or equal to x, and we divide by the total number of points we have. So we have the frequency of points that do not exceed x. If we would have a theoretical probability distribution, we have a similar thing, which is not called empirical. In the case of a probability distribution, it's called a CDF. It is the probability that the random variable takes a value larger than x. It is similar, in fact, it's the same if we interpret here a set of data points as a distribution, which is obtained if we take at random one of the points. If I pick at random a number between 1 and n, uniformly at random, then I have also a probability distribution whose CDF is also exactly this one. And we believe that if the data points come from a certain random instance is a set of instances of a random variable. If they come from a common distribution, then this is an approximation of that. So this is sometimes called the theoretical CDF, and this is the empirical CDF. Now, this is very convenient for comparing and having an idea of the how two different distributions are with respect to each other. Here, for example, I'm plotting the new and the old. We see that the new is to the left. So that means that the values of the new are smaller. For example, if I plot a horizontal line at 0,5, that will give me the corresponding x value that corresponds to 0,5. It's called the median. 50% of the values are below. Being on the left means that the median is smaller here. So in average, but also in complete distribution here, the red is below the blue. So that's a very simple case where the red is really almost entirely on the left of the blue. Of course, like we saw yesterday when we have multi-dimensional metric, and this ECDF is a multi-dimensional metric, there is a value for each data point on the x-axis. Then the comparison may not be complete. So the new might intersect with the blue. But in a case like this, and we have a very clear message, we see that in distribution, the blue is much less than the blue is much larger than the red. So that is a very classical and important tool to use, which gives us a graphical interpretation. Very often, however, we want more synthetic values. We will see a number of them. Let's start with the central values. The central values are the median and the mean. The median I already mentioned. The median is a value such that there is 50% below and 50% above. Now, if n is odd, that gives us exactly what I call x sub parenthesis n plus 1 over 2. So the sub parenthesis means what I obtain when I sort the data points. It's called also, as we will see, the order statistic. So if I sort all my data points, if I have 99 data points, then I sort them from 1 to 99. The one in the middle is 0.50 here. If I have 100 data points, there is 2 points in the middle, 50 and 51. And in that case, you can pick whatever you want, or traditionally, we often take the average of the two here. It doesn't really matter, because typically those two values will be very small. That's the median. Similar to median, there are quartiles. Instead of taking a point that is like here in the middle at 50%, we can take at 25%, or if we're interested in the tail of the distribution, 99 or 95%. Those are called the quantiles of the distribution. So the median in particular is called a centrality measure. It measures what the center of the distribution is. Median is what statisticians prefer, but very often engineers use mean instead of median. The mean is defined by the classical formula. We take the sum and divide by the number. So it's also called the average. Now the average or the mean is graphically harder to get. We don't know from this graph here where the mean is, but for many distributions, the mean and the median are close, but this is not always the case here. Now, the median and the mean give us an idea of where the center of the distribution is. If we're interested in the deviation, so how much dispersion, how much variability there is in this distribution, we can use the quantiles, like I mentioned. Very often also we use the standard deviation. Now there are two churches for standard deviation, the n and the n-1 dogma. So depending on which textbook you read or which formula you use, the two exist. We will see in a few more lectures, in a few more slides, why we have one or the other. In practice, doesn't make a lot of difference because n, the number of samples, is typically large. So the most classical standard deviation is the mean of the square of the distance, of the square distance from the values to the mean itself. M is the mean obtained from this. This sum gives us the sum of the square distance to the mean, and 1 over n is the standard. For some reasons that are true when the data is normally distributed, normally means coming from a Gaussian distribution, this has some interesting properties, but as I said, for the time being, we can ignore the two. Very often also, we're interested in scale-free quantities. So if the thing I'm measuring is x, is in seconds, for example, the mean is in seconds, the standard deviation is in, the square of the standard deviation is in second square, so the standard deviation is also in second. If we rescale the standard deviation by the mean, assuming the mean is positive, we obtain what is called the coefficient of variation. So it has the interest that it is a property of the distribution that gives us the variability independent of the units. So for example, if a distribution is very, very close to the mean, so there is very little variability, then the coefficient of variation will be close to 0. In the extreme case, if there is no variability, all values of x are equal, then xi is equal to m, all values are equal to the mean, and the coefficient of variation is equal to 0. So 0 means that there is no variability. Otherwise, the variability can be any positive value, 1, for example, being for exponential distribution. I'm sure you have seen already the use of the mean and the standard deviation. Perhaps you have seen interpretation like this one. Interpretation one, if I have summarized my data with just those two numbers, the mean and the standard deviation, then with 95% probability, a new data sample would be in this interval, mean plus or minus 196. And similar with other probabilities. What do you think is true? I close the poll in a few seconds. Closing. The majority says none, and with two strong minorities saying A and B. Well, the reality is, well, there is a dependence on assumptions you're making. If the data can be assumed to come from a normal distribution, that means it has been generated by something that produces data according to a normal, that's a synonym for Gaussian distribution, with mean M and variance S squared, standard deviation S. Then, by looking up the tables of the Gaussian distribution, we will find those two things. The probability that X is between the mean and plus or minus 96, the standard deviation, is exactly equal to 0.95. In fact, this is why this number 196 plays a magic role. It corresponds to a 5%, 95% coverage interval for a Gaussian distribution. And if we want 99.9% coverage interval, then we have to go to 3 sigma, roughly 3.3 times the standard deviation. So in some sense, it is true. So if you said A, it is true. B is also true. So the correct answer would be A and B. But this is only if we can assume the data is normally distributed. So this is an assumption that is important because we will need to discuss it. We will see that in the data that we measure, sometimes it is true. A lot of data sets produce data that are normally distributed, but another lot of data sets produce data that are not normally distributed. So we will see several examples of that. If it's not normally distributed, this might be not true, might be grossly wrong if the data deviates a lot from the standard, from a Gaussian distribution here. So the use of the mean and the standard deviation in some sense is intimately related to Gaussian distribution. They say a lot about what is happening in distribution if your data can be thought to be normally distributed. If it is, roughly speaking, normally distributed, those are good summarizations. If they are not, that may be misleading, and we will see that there are a few things to be careful about. So here is an example of how we can summarize the data that we had here in the two plots above, in the scatter plots above. So if I want to summarize the blue cloud of points with the median, then I obtain this red line here. I can do a bit more. I can have the quantiles that are given by the red lines here for the old and for the new. Those are called box plots. And those box plots give us perhaps more synthetic information. They tell us how variable the sets are. And also we see that clearly the new is well below the old here. We can do that for the median and the quantize. This is what typically is done by statisticians, as I said. So this is what the box plot will give you. We can also plot the mean, which I did here, for both. And we will see also that the means are in the same proportion for those examples here. There are other elements on these diagrams that we will discuss in a few seconds. There are many other summarizations that can be used depending on the topic. In data science and in choice theory, for example, people use concepts such as Lorentz curve gap or Gini index. Very often we'll use also Jane's fairness index, which is very similar to the coefficient of variation that I mentioned before, standard deviation divided by the mean. So depending on the paper you use, there may be one or the other type of indices that are used. I will not cover them all in this slideshow, but in the lecture notes you have all details if you need one of them for your project, for example. Now, that was the obvious part, what I said so far. What we can do is we can summarize a given result by computing the mean, the standard deviation, the median, the quantize here. But that's not enough. So a very first important message is that just giving a mean or a median, or also giving a standard deviation, is not enough. What we need to quantify is the uncertainty about the quantity that we're giving. What do I mean by that? Well, here, for example, a box plot will show you not just the value of the median, but we'll put a notch in the box here. And the notch here indicates the confidence we have about the median. So it tells us the median is this value, close to 50, but the exact value is not known. The exact value is somewhere with 95% probability between those two horizontal lines. I can do the same for the mean. I can give some quantification of the uncertainty. So this is the topic of this module that we're seeing, confidence interval. It is about qualifying the accuracy of what we have relative to the variability of the things we have measured. We summarize a large data set with one value. We say old is performing less well than new. And here is the difference in means, for example, but we may also want to quantify by how much we have uncertainty about those values. I talked about the difference. In the specific case that we were looking at, we had two versions of a database management system that produce different execution times for two benchmarks. So an easy thing we can do, instead of comparing the two plots, the two scatter plots, is to match the different points of the benchmarks because they are artificially done. So we can redo the same job with the old and with the new system and compare the performance and plot the difference. This is what I did here. So the scatter plot is for the difference, execution time of a job for one system minus for the other here. So old minus new. So on the y-axis, we have old minus new execution time. That's another way of comparing. And here we will see that, well, it's not always positive, right? So it's not always true that new is better than old. So that's exactly a case where we want to be careful about the summarization. Here, I can plot the histogram, or what I can do here is plot the median. So I plotted here a box plot for this scatter plot, which is for the difference. And the notch, as usual, will give us a confidence interval about the difference. We see the difference is positive, but there is a relatively large uncertainty, and I can do the same for the mean here. So the question, the technical question that we will address now is how do we get those magical confidence intervals? How do we compute them? Well, this is quasi impossible if you do not assume the following. If the data, we have to assume somehow that the data points that we've observed come from an IID model. IID model means what? Well, IID is a term that's relative to a probabilistic model, and it means independent, identically distributed. So independent, identically distributed means that we assume that the data that we've seen, which comes from a complex set of conditions given by nature, by the factors of interest, by the hidden factors, by a number of things. But the way statisticians view this and the way they are able to give quantitative results is to assume that it has been generated by a simulator that has a certain distribution. We will see in the next module how to write simulators that can produce data that follow any distribution. So we can produce a sequence of data that comes from a generator. Identically distributed means the generator is always the same. We always keep the same distribution as the main parameter of the generator. And independent, we've talked about independence last week. Independence means that the information we need when to draw a new sample is only the distribution. The value of the previous sample does not influence at all the next sample that we draw. That's a model. We will talk about this, whether this is true in practice or not. We will see also how we can test when we have a data series, whether it is reasonable to assume that it comes from an ID model. Right now, the important thing to remember is that quasi-invariably, when people are computing confidence intervals or are making predictions or are saying anything in terms of probability, probably they assume that there is an IID model behind it. Given this, so our model is we have a distribution that has a CDF-F. So one way of giving a distribution is to define it CDF, at least if we have a single numerical variable, which for simplicity I'm assuming here. And again, so we assume that the data that we have obtained are drawn from a generator that uses this distribution. Of course, we don't know the distribution. If we know the distribution exactly, then the job is over. So we don't know it. If we had an infinite number of samples, we would know the distribution exactly. But we don't have. We have a finite number of samples. We've seen perhaps 100, perhaps 1 million samples. If the distribution is complex, has many, many parameters, there is a learning thing to do. So exactly what we're doing is, what can we learn about the distribution by seeing a number of samples here? And if we're interested in the median, then there are two things to realize. There are two medians. There is the true median of the distribution. The true median is a value such that with probability 50%, we are below or at this value. Remember, this is the CDF, so that means f of m is a probability that an output of this distribution, x, is less than or equal to m. So if that's 50%, that is what we call the true median of the distribution. Now we don't have the full distribution, but we have only a finite set of points. So what we can do is estimate the median. We have what I call m hat, a point estimate of the median. How can we estimate it? Well, we can use the formula that I gave below. We compute the histogram, we compute the empirical CDF, which means we sort all the data points. And if n is 99, the m hat is the value of the 55th data point in increasing order. The 50th, data point in increasing order, the one that is in the middle of the distribution. That's m hat. The thing to realize that m hat depends on the data. If we do the same experiment twice, since the data is random, we will obtain two sets of data. The estimates of the median will be different. So our estimate of the median is also a random quantity. Hopefully, it is not too random. And this is precisely what a confidence interval is trying to capture. The confidence interval gives us an interval such that with probability, some large quantity, close to 1, very often 95%, sometimes more, sometimes less. If you have more data points, you can go more. If you have fewer data points, like in biology, sometimes you go below. With probability 95%, the method you have for computing your point estimate will be correct in the sense that it will produce an interval such that the true but unknown value is in this interval. So a confidence interval is something that we construct from the data. We have an algorithm that gives us U for the lower bound, V for the upper bound. And like my point estimate, those two bounds are random, but we want a method to compute them such that with large probability, the true value of the median is in the interval. That is a confidence interval. Right? So when we have the box plot here, when we see that the median is given by this, well, the line here at the notch of the box is the estimate, and the amplitude of the two notches is the confidence interval for the median. So that means if we agree with this fact that this data is IID, the true median of the distribution is between the two, is inside the notch here. Where? We don't know, but is inside it. And of course, the width of this interval tells us the uncertainty we have about this median. How do we compute those notches for the box plot? So how do we compute a confidence interval for the median? Well, here is the result. It's very, very little known outside the world of pure statisticians, but although it's very simple, here is the formula. So I'm assuming that I have a set of data points, x1, xn, that are drawn IID from a common CDF. Technical assumption, assume to simplify that it has a density. Most CDFs for us have densities. And I want to find a confidence interval for a quantile. For example, if P is 0.5, that's the median. The method works for any quantile. If we want a confidence interval for the 95th percentile, for example, the method will give also the answer. So there are two ways to look at this result. Let's look at the simpler way, which is approximated, but is simpler to understand. How do I get such a confidence interval? Well, I need to sort my data from smallest to largest in increasing order. Then I compute two indices that depend on two things. They depend on n, the number of data points, and p is 0.5 if we're interested in the median. So I apply this formula that gives me two numbers, j and k. And then my confidence interval is the jth data point to the kth data point. So this is what the theory says. Where do those numbers come from? Well, those numbers are in fact approximations of a condition, which is given here, that has to do with the binomial distribution. The binomial distribution is one standard distribution that you can find by looking up Wikipedia. The binomial distribution is the distribution of the number of successes that you have when you flip a coin. So you have a coin that has probability P of giving what you want, you call it a success, and probability 1 minus P of giving a failure. You try it n times. Out of those n times, you will have between 0 and n successes. In average, you will probably have a number that's close to NP. But the exact distribution is called BNP. So BNP is the CDF of this distribution called the binomial distribution. So this is in theory how you do this. How do we use that in practice? Well, for example, if n equals 10, I have obtained 10 values and I want a confidence interval for the median. Well, what do? I go apply this formula. One way to applying is to go to the table. N equals 10 gives me for the median that the two magic numbers j and k are 2 and 9. That means if I have 10 data points and I want to say something about the median with probability 95%, the only thing I can say is that I can exclude the minimum and the maximum, and the median is in this interval. Of course, if n is 100, we will have a smaller interval. So if we have 100 data points, the same theory will say that the data point with rank 40 and 61 give us the confidence interval for the median. And of course, the larger the n, the smaller this interval will be in relative terms. In fact, we have here an approximate value here in this table. The size of the interval scales like square root of n. So it scales sublinearly. So that's how those things are computed. So first take-home message, one way to summarize what is the central value of a distribution is the median. And giving the median is not enough. We want to quantify the confidence we have in this value, and this method will simply give us the answer. Perhaps some of you are interested in the proof. We won't do many proofs in this course, but here I will do one that will give you an idea of the magic that's behind some of the statistics here. So the idea is the proof is simple. If we remember the model that is used. In this model, we assume that the data points that we have is the output of a simulator. So the simulator is producing a sequence of random variable xi. And one way to understand that is to consider a game done by an oracle who knows the median. Of course, we don't know it, but assume you're the oracle and you know the median value. You look at all the data points that we have seen. If the value of the data point is less than or equal to the median, you declare a success, or you declare a failure. So of course, the probability of a success is 0.5, and the probability of a failure is also 0.5, because M0.5 is precisely the median. Now let n be the random number of successes that I have when I see n equal 10 points. Then we can easily see that if the number of success is 1, this is, whoops. If the number of successes is 1, this means out of the 10 points that I have, only 1 is less than M0.5. Well, that means that the second value, x2, is not less than M0.5 because there was only 1. So the second one, if we want the second one to be less than M0.5, we need that the number of successes is at least 2. So in other words, the event x2 less than M0.5 is equivalent to saying the number of successes seen by this oracle is larger than or equal to 2. We can do the same thing with 9 here. We will see that saying that we have 8 successes or less is exactly saying that the median is strictly less than the 9th value. Now, if the distribution has a PD, as a density, then, as you may know, if you have a continuous random variable with a density, the probability that it takes exactly a certain value is 0. So whether we have strict or large inequality means the same here. So the event that is given here, that x, the second value is less than the value of interest m, the 9th value is larger than the s value here, is the same as saying that whether we have the inequality in the wide sense here. And this is the same as saying that the number of successes is between 2 and 8. The distribution of the number of successes is the binomial distribution with probability with 0.5 of success and number of samples 10 here. So there is no magic. This is where the binomial distribution comes. So if I pick 2 and 8, the probability that the median is between the 2nd and the 9th is equal to exactly this difference here, which comes from the binomial distribution. Why do we do all this thing? Well, if we summarize at the end of the day, what we have is we have a probability like this one that gives us whether my coverage interval, 2 to 9, is good enough, whether I have 95% probability. I can compute this by knowing something that's completely independent of the distribution f here that I had before. So the simulator is producing data from a distribution f that I don't know. I don't know this distribution f. So of course, if I would know f, it's easy to compute all probabilities. But the trick and the magic here is that this formula and this theorem does not require any knowledge of the distribution. We'll see that in order to compute confidence intervals, this is invariably what is done by statisticians, is this to find tricks that give us probabilities that are independent of the specific distribution that we have in mind here. So that was the first part, confidence interval for the median. The proof is perhaps a bit original and tricky, but the method is very simple. You sort the data, you look up in a table, or you use MATLAB to compute the coverage from the binomial distribution, and then you will find your coverage interval for your confidence interval. And statisticians recommend this because, as we will see a bit later, using median is way more robust than using mean and averages and standard deviation. In engineering, however, very often we use mean and standard deviation, so we will also talk about it, and sometimes that's the only thing that's tractable. So let's see how confidence interval for the mean is obtained. Well, the surprising thing is that unlike confidence interval for the median, computing confidence interval for the mean is something a bit tricky that requires additional assumptions. So first, what is a confidence interval for the mean? Well, it's very similar to the median. We assume that we have data that is generated by a simulator that draws from the unknown distribution f. This unknown distribution, we must assume that it has a true mean. So this integral is well defined. There are distributions that don't have a mean. In this case, if you try to estimate the mean of your data sample, you're likely to find things that will be very ugly, like estimates that are very unstable. So we must assume here that this theoretical mean exists. And then we interpret the fact of computing the mean of the sample as being estimating the true mean of the unknown distribution. So we have the theoretical value m hat, so m hat is typically 1 over n sum of the xi here, and that same thing, the confidence interval would be something that the probability that the upper to lower bound, that the true mean is in the interval, is at least 95%. And again, the trick is how can we find an algorithm for computing u and v such that this is true regardless of the distribution f here, like we did for the median here. There is a well-known result that I'm citing here. This result consists in computing the standard mean and the standard variance here. Here we must assume that the distribution from which we are drawing the sample, which is unknown, right, has a finite mean, obviously, because we're estimating the mean, but surprisingly here perhaps, we also must assume that it has a finite variance. We will see that there are distributions, in particular when we measure things on the internet or in data systems, we sometimes find things that are called heavy tail. Some heavy tail distribution have an infinite variance. So we'll talk about what this implies. Here, if we want to compute a confidence interval for the mean, we must assume implicitly or explicitly that the data that we have comes from a distribution with a finite variance. Then we estimate the mean with the formula I mentioned before. We estimate the variance with one of the two formulas I mentioned before. And then we have the following result. Mu n hat, like before, that's the sample mean. That's the mean of the values that I have obtained. So this sample mean is random. So my hat here is for estimation, but perhaps the notation is not showing that very clearly. But the thing to remember is mu n hat is random. Like before, for the median, when we estimate the median of a sample, two different runs of the simulator will produce two different samples and two hopefully slightly different estimates of the median. Here is the same. The estimates of the mean and of the variance will be slightly different. So they are random. So the quantity that is shown here, mu n hat minus mu. So mu is the true but unknown mean, divided by Sn, so the standard deviation, the square root of this formula here, rescaled by square root of n. So this quantity here converges when n gets large to a Gaussian distribution that is standard. And 0, 1, n stand for normal or Gaussian. 0, 1 means standard, means the mean is 0 and the variance is 1 here. And that's the trick. That means that whatever the distribution here, so x is not Gaussian, but whatever the distribution, this rescaled combination of my estimator converges when n is large to something that is always the same, regardless of the distribution of my data point. Of course, we need n to be large. So if we believe that this approximation is good, then we can say this random variable, we can treat it as a Gaussian standard random variable. Therefore, with probability 95%, for example, it will be, this quantity will be between minus 196 and plus 196. We saw that in the quiz a few minutes ago. From the table of the normal distribution, we have this here. So, for example, if I take eta is 196, which means I'm interested in a coverage interval with that is valid with probability 95%, this quantity is between plus or minus 96. With obvious algebra, this is equivalent to saying that the unknown parameter mu, in this quantity, mu n hat and Sn are values we have from the data, and what we don't know is mu. But if we know that this quantity is between two bounds, we can conclude that mu itself is between those two bounds, which by reverting gives mu n hat plus or minus eta Sn over square root of n. So this is the typical confidence interval that is given for the mean. It's a confidence interval because it tells us with probability 95%, approximately when n is large, the true value of the mean is your estimate, and the error bound is proportional to the estimated standard deviation multiplied by the magic number 196 and divided by square root of n. So this is what I did here in the plot. The red line gives us the mean, and the dotted blue lines gives us the uncertainty about the mean about the estimate of the mean. The amplitude of the confidence interval decreases in square root of n. That means when n goes to infinity, it goes to 0, but slowly, like 1 over square root of n. So if I have a huge number of data points, then of course the estimate will be better as expected. At least in theory, because in practice, if I have a huge number of data points, it is unlikely that they are identically distributed for two reasons. Because I have a huge number of data points, either because I did very high resolution measurements. High resolution measurements very often are positively correlated because essentially, if I measure the same thing every microsecond, what I'm measuring now and what I'm measuring 1 microsecond later is in fact almost the same thing. So there is very little independence. So that's one reason for having huge data sets is high resolution. Another reason for having a large data set is we've done a huge experiments that lasted for a long time. For example, I've measured everything on my web server, on my web data center for 1 year. But over 1 year can we assume that things are stationary, that the distribution is the same, and is my data center the same 1 year ago and now? Are the customers the same? Probably not either. So the IID assumption here usually breaks when n is very large. The idea of the proof I've already mentioned. Since we know that this quantity here is approximately a known distribution with probability 95%, it is in this interval, and by inverting this, we find the confidence interval that we want. Well, that is perhaps the other useful information about how to compute a confidence interval. Remember, however, there is a hidden assumption. In particular, we need to estimate the standard deviation, which means the variance here must be estimatable. If it's huge, for example, or if it's infinite, then this formula doesn't make sense. If I have a distribution that would have an infinite variance here, then essentially those values will not give us anything interesting. So there is a hidden assumption that is that of finite variance here. Voila, that's all we will see for today. Short lecture, but it's good to distill those elements in small pieces. We will continue next week about confidence intervals. There will also be a quiz next week that I will invite you to do about confidence intervals. If you have not finished the quiz of yesterday, please think about doing it. And then you can already, without further ado, you can start with the lab that for this first lab will not require computing confidence intervals. So you can already start immediately with the first lab. Thank you very much. We will continue to be online, and we will respond to you, answer your question, any questions you might have about the labs in the coming 2 hours.